Okay, let's get started. And as we probably mentioned this week, this week we are basically finished what we want to taught the class. So this week, just before final, we are going to do something special. So I think today I will go over. So maybe both today and Thursday will be a bit shorter. So today I will talk about this IBM IBM Composer and the QSGate. This is where you can try to run quantum simulation on these IBM's free online resources. And on Thursday we will basically just give a final review. Okay. And next week we'll have our final. Okay. And so today we'll talk about this IBM Quantum Composer. And so this is a bit of outdated. I think the results actually get fewer because I think IBM is trying to generate some revenue. And so we have this anyway, so we have this tutorial that posted on eLearn, and it says go to this IBM Quantum Lab website. And unfortunately, Quantum Lab is no longer available, but the composer part is still here, so we can use this. Okay, and so this is IBM Quantum Composer. And okay, so so if you are so maybe let me sign out. Okay, so so this is IBM Lab. Sorry. And then if you don't have an ID, then you can create an ID and sign in yourself. But okay, so this is a bit annoying. Right? So you can sign in yourself and then log in. And once you log in, then as we said, there is this composer file. Composer tab you can go to, and you will have this thing. Okay. And so you should go to sign in, and you need to go to learning, and it's a bit weird. And in the learning tab, then you can click on the composer. Okay, and then you get to composer, and also instance close. Okay. Maybe just use this one. Okay, and then you can create different composer file. Okay, let me try reloading. And so you can have a different composer file, and today we are using this class file. And so this is a very nice graphical interface here. Okay, so let me start. So here you see we have 2 qubit system, and so qubit 1, qubit 2, and we are creating an EPR pair here. So here we have a headma and a C naught, and then we measure the first qubit and then measure the second qubit. Then you see that here we have the measurement result says that you have 0 at a 50% probability and 1 at a 50% probability. And we have a different different presentation. So that was probability, and okay, so this is a bit funny. We'll talk about this later. And there are different presentations, state vector and Q sphere. And then so here is a graphical interface, and here are the corresponding code here. So this code what this code this graphic represent. So here we have headma on Q0, so maybe I try this headma on Q1, then you see the headma move here. Okay, so you can also edit code here to change the graphical interface. And yeah, so you see this is a very nice thing. And if I delete this, okay, and let's try to kind of go in reverse order. And so I can just left click this and delete. And okay, so it's a bit funny. And then you see that we have then instead of for the measurement on this C, then you have a measurement result here, and this is a bit native here. Okay, and yeah, so that's a quick showing of how this works, and let's try to go into more detail. And so if you, I think I recommend using the GUI here to do editing, because the this year when I try this, if you edit it here directly, it's a bit buggy. But hopefully it's getting better. But anyway, so you can do everything very nicely with the graphical interface here. So here we start with some quantum register and some classical register. And if you want to add the quantum register, you can just add, and then you can add the classical register. Classical register is just all add to the same line here. But if you want to have the yeah, it's better to have just same line here, but you can also add a separate classical register, but it will get a bit messy. Okay, so let's delete this register. And even better way is if you click these three dots, and you can have management register, and then you see that then you have a very nice result here, very nice interface here. So you have quantum registers and the classical registers, and you can add a register. And yeah, so give names like Q2, Q1, and more qubit, etc. And you can add more classical register. It's a bit troublesome, as we will say later. Okay, so you can edit just the number of classical wire here, and also edit number of quantum wire here, and okay. And yeah, so you have kind of quantum register, and this is a different name. But I think this also looks a little ugly, so you just have some quantum qubit and some classical qubit like this. Okay, and yeah, so that's getting the starting state. Okay, and so everything is start with 0, and then you want to apply your gates here. And so you can see you have a whole bunch of gates here. So we have headma gate. This will turn a 0 to plus state. So you see 0 turning to plus state. So you have this. Okay, so we have too many. Let's delete some. Okay, maybe delete all those. Okay, so we start with 1 qubit and some classical register that can be used in measurement. Okay, and so you see the headma state turn your state into 0, 0. So at the end state, you have 50%. You have amplitude 1 by square root to 0, 1 by square root to 1. Okay, and if you do measurement, the probability is 50 and 50. And we also have this funny Q sphere representation. So it says sphere, but this is actually not blood sphere. This is some weird representation that IBM give. But you see, so you have something 0, something 1. And then let's do this. Okay, so maybe the phase gate. Okay, and then you can have headma, and then you can have z gate. And so it was 0 plus 1, and then after z gate it will be 0 minus 1. And it's representing this 0 minus 1 with this color. So the phase is color. So 0 is blue. So excuse me. 0 is blue, so phase angle was 0. I cannot really point here, but you can see the angle saying 0 here, and it's red, and phase angle is pi. And here you also see 0, 0 with blue, and 1 with pi. So this sphere thing is actually just this vector thing, but having each computational basis state in somewhere on the sphere. So this is a bit funny. It looks like block sphere, but it's not block sphere. And so it's a Hedman gate, Z gate. Then we also have, I think this is S gate. So if you do a S gate, then you will swap between 0 and 1. So you see the 0, 1, and 1 swap. So 0 has phase pi, and the 1 has phase 0. And you see here the phase swap. And if you go to probability, then it's still 0, 0. Okay? And so let's try more single qubit gate. So the identity is, well, its identity does nothing. It's just some placeholder thing. Okay? And you can have T gate. This will further shift your phase. So you have pi over 4 on the second, on the 1. Okay, so T gate, you have T gate everywhere differently. Okay, so this is T gate, and S gate, another phase. Phase is pi over 2. And and Z gate was that. Then you have inverse T gate. This will give you minus 5 over 4, minus pi over 4 phase on the 1. And you have A stagger, so this should give you minus I phase, so it phase become 3 pi over 2. And P gate is, I think P is same as T. P gate, P gate is same as P gate is something, okay, so it's something funny. Okay, so P gate is actually phase gate, but it has an extra parameter. So here the parameter is pi over 2, but you can just have arbitrary rotation here. So maybe you have like pi over 3 here, and then this will become pi over 3. Okay, so this is something with parameter. Okay, and this is something we want to talk about. So some of those gates here, you can have parameter. So say the P phase gate, so if you just double click and it will give you this interface. Or you can click this edit. Okay, or you can right click it and click edit, and it will bring up this interface that let you set a different parameter on your gate. Okay, so here we can set, because this P gate has an angle, so you can set what's the rotation angle here. Okay, and let's delete this, and I think let's delete this, and then RZ gate I think is similar. So RZ gate I think just same as P gate actually. So you do some Z rotation, and pi over 2, and pi over 3, and etc. pi over 4. So you can see different color, or just pi, etc. Okay, so those are single qubit gate, and let's add extra qubit, and let's have the probability, and let's add extra qubit, and see some 2 qubit gate. Okay. And you see, so let's have our universal gate set. Okay, and maybe delete. I think it's okay. Then we can have our C naught here. Okay, so C naught here. Then you see we start with the Hedema, and then C naught gate. And so up here is Bell basis state, and then you could do some poly to change your Bell basis state. Okay, Bell state. So I have let's start with the thing. Okay, so this is 0, 0 plus 1, 1 with the same phase, and then if you put let's see, I don't even remember. So you put a X gate here, then it becomes 0, 1 plus 1, 0, and they put a Z gate here. Then this becomes 0, 0 minus 1, 1, and you can put both Z and X, and then you have this 1, 0 minus 0, 1, or if you change your order, okay, change your order, then you have 0, 1 minus 1, 0. Okay, so you can have, you can have all 4 Bell basis state here. It's pretty cool. And also you can put maybe plus state here, then it's a different thing. Okay, and if you measure in computational basis, this is 0, 0, 0, 0, 1, 1, and if here, then it's 0, 1, 1, 0, etc. Okay, so you can have a Bell state here, and so this is a 2 qubit gate, and let's do something funny. Okay, so we have let's talk about this. Okay, so 2 qubit gate, and then when we drag here, we just have control here and the target here, And if you want to swap the control and target, then you need to open up this this edit menu, and okay, remove control. Sorry, edit control. Okay, and yeah, so you need to swap the control and the qubit gate, control and target, and then you just choose here. So this will swap the control and target, and if I add one more qubit, then I can we can say the control to the second qubit, etc. But I think if you say the control to the target qubit, you will just swap between them. Okay, and swap back to this one, and let's delete this one. Okay, so it's simpler. Okay, so that's how you change the control. That's how you change the control and target of 2 qubit gate, and then you can also have this is swap gate. To show that it's swap gate, maybe I'll start with this. Okay, no, not this one. Let's see, maybe Z gate. Okay, so it was a 0 0 minus 1 1, and if I do swap, I think it will swap something. No, let's see. Maybe I need both X and Z. Okay, so I have 0 1. So maybe this one. So I have 0 1 minus 1 0, and if I do swap gate, it should be okay. So you see the red and the blue swap. Okay, so it was 0 1 minus 1 0, and now it's minus 0 1 plus 1 0. Okay, so this is a swap gate. It is swap the first qubit with the second qubit. Okay, and then here we have a middle. Okay, so the red gate are a bit more weird. So this is a Y gate, and then this is rotation X with some angle, rotation Y with some angle, okay, and the worth of a square root of X, etc. So what's this? Okay, so this is rotation of XX. Okay, so those are weirder gates, but you can try yourself. Let me try what's even U. U is a very weird 1 qubit gate. It's this is you have a 3 angle, so this is this is rotation on the Planck sphere with the 3 angle theta, phi, and lambda, and you can figure out yourself what's theta, line, and phi, lambda. Okay, but let's start with let's keep to ourselves to either case. Okay, so we have Sina, Hendma, Polis, and the T and the P, etc. And if we add one more qubit, I think there is a 3 qubit gate. Then it's a Toffoli gate. So this is a control node. Yeah. Let me see if I do it here. Maybe it's more useful. Yeah. So you can have Toffoli gate to do things. It will control on the first 2 qubit, and then on the third qubit, etc. So if I delete this, then we can see what the Toffoli do. So it was put at the beginning. So this was okay. So let me delete this. Okay. So it was okay. This counting is a bit funny. So 0 is actually the last qubit. So last qubit was 0, and it was 0 0 0 and 0 1 1 here. And if I add Toffoli, then you will say when the first 2 qubit are 1, then the third qubit also become 1. So it becomes 0 0 0 and 1 1 1, etc. Okay. So this is Toffoli, and I think I can also put Z somewhere to change its phase. Do Z here will change phase. Do Z here it does nothing, etc. And if I do X somewhere, this will be funny. Yeah. So do X here, and it will X a different part, it change to a different state. Okay. And so those are gates, and you can explore the different options for gates. Okay. And then there are weirder things. Okay. Then there are those gray things, and I don't want to tell too many of them. Let's see when I try this if it was buggy, but anyway, there are some conditional things you can try here. But the one I really want to talk about is this measurement. Okay, so you can measurement and so as you see, you can drag the measurement here. So this is the measurement side, and they only do computational basis measurement. Okay, if you want to do different basis measurement, then you need to edit your circuit before to change it to a basis you want to measure. And so this thing will do. What you do is you measure the first qubit onto the first classical on the zeros classical register here. And so you can have more measurement here, and this will measure the second qubit to the second classical register here. And so here is some interface issue. So you see that once we place the measurement operator here, then the state vector no longer tells you anything. So I think this is just what this system is designed. Okay, so if you put any measurement operator in your circuit, then it will no longer represent the state vector end. So you just set the state vector to default. And so what you need to read is, but the probability here is still good. So probability is you measure this thing, and you measure this first qubit, and they will give you some 0, 1, and it's stored here. Okay. So this output is now saying what this classical register tells you. And okay, so there was something. Actually, I'm not sure. I want to try now. Okay, so right now this classical register is 2 qubit. So you're just saying what's this? No, sorry, not 2 qubit, 2 bits here. So this let's go back to manager. Okay, so this is 2 bits here. And so this is what's the probability of those 2 bits after you set in the measurement result. And it was so it was 4 possibilities: 0, 0, 0, 1, 1, 0, and 1, 1. And because you add this 50% to the first qubit, and the first qubit also actually on the is this qubit. Sorry, the first qubit is actually the number on the left here. So you see it's 50% being this bit being 0, 50% being 1. And the second qubit, which is the leftmost one, is always 0 here. And let's say if you do also measurement result here, then you see here, yeah, so the 2 qubit, the 2 classical bit will will be like the previous measurement result. So it's a 50% 0, 0 and a 50% 1, 1. And but if you see the number here, it's actually not perfect 50% because I think this is actually run by simulation. So so what the simulator do is it actually try to run this circuit many times and do measurement and have the probability as the probability is calculated as okay. So you can see this 1024 shots. So it will run this circuit 1024 shots, and then record the probability as histogram here. So you see it's a slightly of 50%, and you want to try different things, so you can change your random seed here, and I think that will change your probability. So you can try different random seed, and then the probability should change. Let's say if I have 1, 2, 3, 4. Yeah, so the probability change, and some of the state vector also change. I'm not very sure why, but I think it should not get a state vector. Oh, I see. So state vector is probably a random one you get. But anyway, not very important. Anyway, you have a measurement here, and the state vector is going to be very weird. It's one of the states that you get after you do measurement. Okay. And yeah. And I think the probability is anything between 0 and 9999. And yeah, so you can change that, and oh, this is a very good seed. Okay, so this seed you have 50%, 50%. Then you have this, then you have different seeds, and you have different probability, etc. Okay, and yeah, so that's state creation and getting circuit and then getting measurement. Okay, and but those are all on simulation. And if you want to, so I think then let's talk about something funny. Okay, and So this is that. And there is some high level thing you can do is you can try to group them together and create I think it kind of create a macro. Okay, let's see. Yeah, so you can do this group operation. And so let me say bail. Okay. So must start with lowercase. Sorry, bail. Okay. Yeah. So you can actually create this group, and then it will become your count here. Okay. So you can have several of those groups together. So if you want to draw something very complicated here, then yeah, then you can create those group operation, and then yeah, sorry, then yeah. So you can kind of create kind of a black box one. You can think of this kind of a black box, then you see that you create all sort of thing. Okay. Let's delete this so the state vector is correct. Okay. So you see you can have a whole bunch of those black box. So this is when you want to create something very complicated, then you can have this group function. And I think if you don't want this, then I'm going to do something dangerous. So let's see, I think I can remove this thing, and yeah, then those are all removed. Okay, and then I think the next part I want to talk about is I can edit the, I can also edit the gates directly here. So say this is Control X here, then I can say change so this is a control and the target, so you can swap the control and target by just changing code here. So here is saying the control target is the same, so I have compiler error, then change this, yeah, then control and target will swap to each other. Okay, and then let me also try something funny. So if I delete this, and if I create HR register, oh, not this, not like this. So if I create a HR register after this thing, and okay, and I do measurement, then yeah, and then I have a lot of results. Okay, so it's putting all the register here. So measurement, manage register. So if I just 1 qubit here, 1 bit here, okay, then yeah, then you see you have a 3-bit result, etc. Okay. But yeah, then you have a measurement result to different parts, etc. And but this will make it a little weird. So let's just have one register with many bits. Okay, and then so this is like an online simulator of how you control a quantum circuit to see how it goes. And if you want to actually run this on quantum computer, actually can. So that's where you click this setup and run. Okay, and yeah, so I think we have a pretty good circuit here. Okay, so you just click setup and run. Then you go to this interface of you can choose which processor to run on. Okay, so here we have some spec of the processor. So you have a number of qubit and what's the area of those processors. So you see, they're actually all pretty big. I don't know why they don't. Anyway, yeah, so there are all 127 qubits, so those are all really big processors, and and then you have different error rate, so they are all on order of 10 to the minus 2, and then also different speed. Some of these ones is much faster. Okay, so the C-LAPS is basically the speed of the processor, and then you can see the bridge span one is much faster. Okay, so you can choose your processor. Let's choose the fastest one, and yeah, then you have a different instance, and you can choose the number of shots. So basically, you want to run how many times of your processor. So here we are pretty short, so we just run 10 times. But to get more statistically significant, maybe you want to run 1,000 times. Let's start with something short, maybe 100. Okay, and yeah, so you just click run, and you will run. Okay, and So it's running, and so you have job sent here. So you can click on here, and you will see the job run. Okay, but it's pretty slow. So I was sending a job just before the class. So last night I sent something. Okay, so this is completely result, and yeah, then you can see the measurement result. Okay. But this is a bit funny, so this is why I say don't run two different classical registers. I guess this is something important for us to know also. Okay, let's change this a little bit. Sorry. Yeah. So I was running this build circuit and I want to see 0, 0 and 1, 1, but I see two histogram of 0, 1 because I have two classical registers. So apparently, if you have two different classical registers, then you will get a result on the different registers separately. So don't do that. So this result was done by the circuit. Let me try to reproduce that. This result was done on a circuit that look like this one. Okay. If you do this, this circuit, although this look like 0, 0 and 0, 1 here, I guess, yeah. Yeah, so it will be 0, 0 and 0, 1 with 50%, 50%. And so probability, let's see if I can see 0, C0, 0, C0, 0, yeah. And yeah, so you actually don't see 0, 0 plus 1, 1 here, so it's a bit funny. So if I edit this one and make it 2 and make this thing, okay, so I cannot just use drag to change this. I need to actually edit, and so cbit I get this thing. Wait, why is this doing that? Oh, I forgot to swap this. Okay, so I swap this thing. Sorry. Okay, sorry, I was confusing myself. Okay, I was wondering why it's not build state because I swapped it and forgot to change it back. Okay, and yeah, so this is 0, 0, 1, 1. Okay, and you see register, and I do this. Okay, and yeah, so this was looking like it will be okay. Let's change this back. Okay. So you think if you have two different classical registers, it's not a problem because you also have 0 and 1, 0, 0 and 1, 1 here in this histogram. But unfortunately, if you run it as a job, then you get two marginal distribution. You get first register was a 50% 0, 50% 1, and the second register is also 50% 0, 50% 1. But then you don't see the correlation of this 0, 0 and 1, 1, and that's pretty annoying. Okay, and but anyway, so you can see the detail here, and I think you can also download the result as some format. Where's the download result? See more details probably. No, job complete simpler. So you can see we use 2 seconds on its processor to run this 10 times. And yeah, total completion time was actually even hours because you just need to wait in a line for a really long time. Okay, yeah, so the measurement result and the circuit, I don't think my circuit is, oh okay, yeah, and this is the intro circuit I run. It's a lot more complicated because I think the headmap you actually need to do different things to do headmap. Okay, so this is the intro circuit he run. So yeah, so this is probably the so headmap you need to do weird things to do headmap, and control nut you also need to do weird things to get control nut. Okay, and yeah, and it's 127 qubit. So you are not using 125 of them, okay? And you have 2 of them, and you run something, then you measure it. and wasting a lot of computation resource. And yeah, this is a job result. Yeah, and I think you need to write this QSkit runtime to you can use this code to retrieve your result. Okay, and yeah, if you run some local QSkit code. Okay, and but that's more complicated for now. QASM and yeah, QSkit. Okay, so those are just circuit, yeah, circuit result. Okay, and so that's the result, and so here we go to bake jobs, and well, it takes average 11 hours. So this is just 1 hour ago, 21 minutes ago. We still need to wait in the line for a lot of time. Okay, and yeah, and about the IBM resource, I think. The free version is actually getting not too much resource now, so we actually only have 10 minutes of total computation time on the 10 minutes of the total computation time per month, so it's pretty little. But I think you can get your hand on, try a little bit of computation to do. And obviously, if you want more computation time, you need to upgrade the program here. Okay. And yeah, instance QPU, so that's the online computer they use. They are open to free use. I think it's for now it's just 3 of them. And yeah, so here are the list of the actually list of the QPU they have. So they have the 11, so basically quantum computer here, and only 3 of them are available for public. So 3 of the 127 ones. And but it's a lot of improvement. I'm not sure it's improvement or disprovement. So previously they have some quantum computer with that's pretty small, like 5 to 20 qubits, etc. But now every computer is about 100, is more than 100 qubits. So they are all pretty large computers. And I think you can, okay, and yeah, so those are locked. So I think those are only for paid members. And yeah, so the free public one are those 3, and you can see they are pretty competitive. And I think here, can we see, so we have more data, okay, yeah. And here you can see the connectivity graph of the computers. Okay, so it's like this. So actually, not every one of them are connected, but yeah, the 127 qubits are connected in this way. But yeah, and we also can see collaboration data on each qubit. So I think if it's a darker color, then it has less error. So those are like 10 to the minus 2, 10 to the minus 3, and but those lighter color one are the more. Oh, so I think you can click on the edge and the qubit to see different errors. So those are 2 qubit error, actually pretty small. So this is 10 to the minus 3. And then yeah, but you have some qubits that's worse. So those are error 10 to the minus 1. So this is actually pretty worse, pretty bad. This is 15% error. And say this one, yeah, this is all about 15% error. So it's a bigger error. Yeah, so you will try to optimize your program on this connectivity graph and run it. And I think also for the free for the free plan, you can only draw at most 7 qubit. And yeah, so it's pretty limited, but I think it's a nice thing you can try yourself. So you can run this quantum computing. You can control some simple program up to 7 qubit with this composer and send it to one of the free online quantum computers to run and see your result. Okay. And yeah, so but you see you have a limited number of qubit and a limited computation time. But yeah, it's nice we have this free open online resource here. Okay. Yeah, And but I think if you want to send a job, then you also need to complete the you need to create an account and have it sign in. But for just the composer, you can even do without creating an account and sign in. Just do it. just go to this website and go to the composer, and you can try to drag the different gate on the circuit, and you can see the state vector. I think it's pretty cool, and hopefully give you some intuition about quantum computing. Okay. And we have about 10 minutes left, but I think I complete what I want to say. So let's see if anyone has any question about this IBM quantum learning. Otherwise, we will stop early today. Okay? People good? Yeah. Then if we are fine, then we can stop early, and see you next week. No, not next week. See you on Thursday, and we'll talk about finals. Okay, so see you on Thursday.